Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. When Earth casts its shadow across the lunar surface, transforming our familiar silver moon into a haunting crimson orb, we witness one of nature's most spectacular celestial performances. The total lunar eclipse, often called a blood moon, represents a precise astronomical alignment that has captivated humanity for millennia. A lunar eclipse occurs when Earth positions itself directly between the Sun and Moon, blocking sunlight from reaching the lunar surface. This phenomenon can only happen during a full moon, when our natural satellite sits on the opposite side of Earth from the Sun. However, not every full moon produces an eclipse. The Moon's orbital path around Earth tilts approximately 5 degrees relative to Earth's orbital plane around the Sun, called the ecliptic. This inclination means the Moon usually passes slightly above or below Earth's shadow cone during full moon phases. For a total lunar eclipse to occur, the Moon must cross the ecliptic plane at precisely the right moment, aligning with Earth and the Sun in what astronomers call syzygy. These crossing points, known as nodes, experience eclipse seasons approximately every 6 months. During these windows lasting about 34 days, lunar eclipses become possible. Earth's shadow consists of 2 distinct regions. The umbra represents the inner, darker shadow, where Earth completely blocks direct sunlight. The penumbra forms the outer, lighter shadow, where Earth only partially obscures the Sun. As the Moon enters the penumbra, observers notice a subtle darkening on the lunar surface. This penumbral phase often goes undetected by casual observers, because the dimming appears gradual and relatively faint. The dramatic transformation begins when the Moon enters the umbra. Earth's shadow slowly creeps across the lunar surface, creating a curved boundary that ancient Greek astronomers recognized as evidence for Earth's spherical shape. This progression takes approximately 1 hour as the umbral shadow engulfs the Moon completely. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. During totality, the Moon doesn't disappear entirely. Instead, it glows with an eerie reddish hue that can range from bright copper to deep burgundy. This coloration results from Earth's atmospheric refraction of sunlight. While Earth blocks direct sunlight from reaching the Moon, our atmosphere acts like a lens, bending red wavelengths around our planet's edge. Blue light scatters more readily in Earth's atmosphere, explaining why sunsets appear red and why the eclipsed Moon takes on similar coloration. The intensity and exact color of the blood moon depends on atmospheric conditions on Earth. Volcanic eruptions, dust storms, and pollution can affect how much light reaches the Moon during totality. The Danjon scale, developed by French astronomer André Danjon in 1951, classifies lunar eclipse brightness from 0, representing very dark eclipses where the Moon nearly disappears, to 4, indicating bright copper-red eclipses. Total. Lunar eclipses occur roughly twice per year on average, but visibility depends on geographic location. Unlike solar eclipses, which require observers to be within the Moon's shadow path, lunar eclipses can be seen from anywhere on Earth's nighttime side. This accessibility makes lunar eclipses more commonly observed than their solar counterparts. The duration of totality varies significantly between eclipses. When the Moon passes through the center of Earth's shadow, totality can last up to 1 hour and 47 minutes. However, when the Moon skims the edge of the umbra, totality might last only minutes. The Moon's elliptical orbit also affects eclipse duration, with longer eclipses occurring when the Moon is farther from Earth and moving more slowly in its orbit. Understanding lunar eclipses requires appreciating the delicate balance of celestial mechanics that govern our solar system's dance. Earth's shadow extends approximately 1.4 million kilometers into space, creating a cone-shaped region of darkness that the Moon occasionally encounters. This shadow structure determines every aspect of a lunar eclipse's appearance and duration. The geometry of Earth's shadow results from our planet's size relative to the Sun and the distance between Earth and Moon. The umbra, Earth's complete shadow, measures approximately 9,100 kilometers in diameter, at the Moon's orbital distance of 384,400 kilometers. This measurement explains why total lunar eclipses can last nearly 2 hours. The Moon, with a diameter of 3,474 kilometers, fits comfortably within the umbral cone, allowing for extended totality periods. The penumbra extends much farther, creating a gradual transition zone where Earth partially blocks sunlight. This region measures approximately 16,000 kilometers in diameter at lunar distance. As the Moon enters the penumbra, observers notice subtle darkening that becomes more pronounced as the lunar surface approaches the umbral boundary. Professional astronomers and dedicated observers can detect penumbral eclipses, even when the Moon never enters the umbra. Earth's atmosphere complicates the shadow's geometry through refraction. Our atmosphere bends light rays, effectively expanding the umbral shadow by approximately 2%. This atmospheric effect, discovered through precise eclipse timing measurements, means the geometric umbra slightly underestimates the actual shadow size. Additionally, Earth's atmosphere absorbs different wavelengths unequally, contributing to the blood moon's characteristic coloration. The Moon's orbital velocity determines how quickly it traverses Earth's shadow. At perigee, when the Moon sits closest to Earth at approximately 356,500 kilometers, it moves at roughly 1.08 kilometers per second. At apogee, the farthest point at 406,700 kilometers, the Moon slows to approximately 0.96 kilometers per second. These velocity variations affect eclipse duration significantly. Eclipses occurring near apogee produce longer totality because the Moon moves more slowly through the shadow. The longest possible total lunar eclipse, lasting 1 hour and 47 minutes, occurs when the Moon passes centrally through the umbra at apogee. Conversely, eclipses near perigee, when the Moon appears larger and moves faster, produce shorter totality periods. The Moon's orbital inclination of 5.14, 5 degrees relative to the ecliptic, determines eclipse frequency and characteristics. This inclination means the Moon's shadow typically passes above or below Earth during new moon phases, preventing monthly solar eclipses. Similarly, Earth's shadow usually misses the Moon during full moon phases. Only when the Moon crosses the ecliptic plane near full or new moon do eclipses occur. The ascending and descending nodes, where the Moon's orbit intersects the ecliptic, precess slowly due to gravitational perturbations from the Sun and Earth's equatorial bulge. This precession causes eclipse seasons to occur approximately 19 days earlier each year. The complete cycle, called the regression of nodes, takes 18.6 years to complete. Eclipse cycles result from the complex interplay between the Moon's orbital period, Earth's orbital period, and the regression of nodes. The most famous cycle, the Saros, discovered by ancient Babylonian astronomers, repeats every 18 years, 11 days, and 8 hours. After one Saros cycle, the Sun, Earth, and Moon return to nearly identical relative positions, producing similar eclipses. Each Saros series contains approximately 70 eclipses, spanning about 1,200 years. Early eclipses in a series are partial, becoming total as the Moon's path shifts to pass more centrally through Earth's shadow. Eventually, the path shifts again, producing partial eclipses before the series ends. Modern eclipse prediction relies on precise orbital calculations considering gravitational perturbations from planets, the Sun's gravitational field variations, and relativistic effects. NASA's eclipse prediction algorithms can accurately forecast eclipses thousands of years into the future and past, allowing historians to correlate ancient records with specific eclipse events. The mathematical precision required for eclipse prediction demonstrates humanity's advanced understanding of celestial mechanics and our ability to model complex gravitational systems with extraordinary accuracy. The transformation of the Moon from silver to crimson during totality represents one of Earth's most beautiful demonstrations of atmospheric physics. This color change results from the same phenomenon that paints sunsets red and makes the sky blue, the interaction of sunlight with Earth's atmosphere through scattering and refraction. When sunlight encounters Earth's atmosphere during a lunar eclipse, molecules and particles scatter different wavelengths unequally. Blue light, with its shorter wavelength of approximately 450 nanometers, scatters more readily than red light at 650 nanometers. This selective scattering, described by Lord Rayleigh's mathematical formulation in 1871, explains why Earth's sky appears blue during daylight. During a lunar eclipse, Earth's atmosphere acts as a massive lens system, refracting red wavelengths around our planet's curved edge. While blue light scatters away into space, red wavelengths bend through the atmosphere and continue toward the moon. This refracted red light illuminates the lunar surface during totality, creating the blood moon effect. The amount of refraction depends on atmospheric density and composition. Earth's atmosphere is denser at lower altitudes, causing greater refraction near the horizon. Temperature gradients, humidity levels, and atmospheric pressure variations all influence how effectively Earth's atmosphere transmits red wavelengths to the eclipsed moon. Volcanic eruptions significantly impact blood moon coloration by injecting particles into the stratosphere. The 1815 eruption of Mount Tambora in Indonesia produced exceptionally dark lunar eclipses for several years. Similarly, the 1991 eruption of Mount Pinatubo in the Philippines caused notably dim lunar eclipses throughout the early 1990s. Atmospheric pollution also affects eclipse coloration. Industrial emissions, wildfire smoke, and dust storms can alter the moon's appearance during totality. Cities with significant air pollution often report darker, more brownish lunar eclipses compared to observations from rural locations with cleaner air. The Danjon scale quantifies lunar eclipse brightness using 5 categories. Level 0 eclipses appear very dark, with the moon barely visible and often brownish-gray in color. Level 1 eclipses show dark gray or brown coloration with surface details difficult to distinguish. Level 2 eclipses display deep red or rust coloration with a darker umbral edge. Level 3 eclipses appear bright copper red, often with a bluish umbral border. Level 4 eclipses, the brightest category, show orange or bright copper coloration with a blue umbral edge. Historical records reveal how ancient civilizations interpreted blood moons. Mesopotamian astronomers maintained detailed eclipse records, recognizing eclipse cycles and developing prediction methods. Chinese astronomers described lunar eclipses as a celestial dragon devouring the moon, leading to ceremonial attempts to frighten the creature away through noise and celebration. Greek philosophers used lunar eclipses to deduce Earth's spherical shape. Aristotle noted in the 4th century BCE that Earth's shadow on the moon always appeared circular, regardless of the eclipse's timing or the moon's position in the sky. This observation provided strong evidence against flat Earth theories, prevalent in ancient times. Christopher Columbus famously exploited knowledge of a predicted lunar eclipse during his 4th voyage to the Americas. Stranded in Jamaica in 1504, Columbus consulted astronomical tables predicting a total lunar eclipse. He warned local inhabitants that his god would darken the moon if they didn't provide supplies. When the eclipse occurred as predicted, the impressed locals agreed to Columbus's demands. Modern spectroscopic analysis of eclipsed moonlight reveals detailed information about Earth's atmospheric composition. By studying which wavelengths reach the moon during totality, scientists can analyze ozone concentrations, water vapor levels, and aerosol distributions in Earth's atmosphere. This technique provides a unique perspective on our planet's atmospheric properties from space. The blood moon phenomenon demonstrates how celestial events can illuminate fundamental physical principles connecting ancient observations with modern atmospheric science and revealing the interconnected nature of Earth's atmospheric and astronomical systems. The regularity of eclipse patterns fascinated ancient astronomers, leading to sophisticated mathematical systems for predicting these celestial events thousands of years before modern computers existed. The discovery and understanding of eclipse cycles represents one of humanity's greatest early scientific achievements, demonstrating our ancestors' remarkable observational skills and mathematical insight. The Saros cycle, the most famous eclipse period, spans 18 years, 11 days, and approximately 8 hours. This cycle results from the complex relationship between three fundamental lunar periods: the synodic month of 29.5306 days, during which the moon completes its phases, the draconic month of 27.2122 days, representing the time between successive passages through the same node, and the anomalistic month of 27.5546 days, marking the time between successive perigee passages. Ancient Babylonian astronomers discovered that 223 synodic months nearly equal 242 draconic months and 239 anomalistic months. This mathematical relationship means that after one Saros period, the Sun, Earth and Moon return to very similar relative positions, producing eclipses with comparable characteristics. However, the Saros cycle's 8-hour offset means successive. Eclipses in the same series occur approximately 120 degrees westward around Earth. After 3 Saros periods, spanning 54 years and 34 days, eclipses return to roughly the same geographic region. This triple Saros period, called an exeligmos by ancient Greek astronomers, provided a more practical prediction tool for local eclipse forecasting. Each Saros series contains approximately 70 to 80 eclipses spanning 12 to 13 centuries. The series begins with small partial eclipses occurring near Earth's polar regions. As centuries pass, the eclipse path migrates toward the equator, producing larger partial eclipses, then total eclipses, before eventually returning to small partial eclipses at the opposite pole as the series concludes. Saros Series 136, currently producing some of the longest total lunar eclipses, began in 1358 CE with a small partial eclipse. This series will continue producing eclipses until 2618 CE, demonstrating the remarkable longevity of these celestial patterns. The Metonic cycle, discovered by Greek astronomer Meton in 432 BCE, represents another important eclipse relationship. This 19-year period contains exactly 235 synodic months, after which lunar phases repeat on nearly the same calendar dates. While not as precise as the Saros for eclipse prediction, the Metonic cycle helped ancient civilizations align lunar and solar calendars. Modern eclipse prediction employs sophisticated mathematical models considering gravitational perturbations from all planets, the Sun's varying gravitational field, tidal forces, and relativistic effects. NASA's eclipse prediction algorithms, developed primarily by Fred Espenak and Jean Mears, can calculate eclipse circumstances with extraordinary precision, extending thousands of years into the past and future. These calculations reveal that Earth currently experiences approximately 2.4 lunar eclipses annually, on average. However, this rate varies over long periods due to gravitational perturbations affecting the Moon's orbital elements. During some years, no lunar eclipses occur, while other years feature up to 5 lunar eclipses, though such maximum years are extremely rare. The next several years offer excellent opportunities for lunar eclipse observation. 2025 features 2 total lunar eclipses, one on March 14th, visible from the Americas, Europe and Africa, and another on September 7th, observable from Europe, Africa, Asia and Australia. These eclipses belong to different Saros series, demonstrating how multiple eclipse families operate simultaneously. 2026 will present 2 partial lunar eclipses, followed by 2027's single total lunar eclipse on February 28th, visible primarily from the Americas and Western Europe. This eclipse promises exceptional viewing conditions for North American observers, occurring during convenient evening hours. Long-term eclipse predictions reveal fascinating patterns extending far into the future. The Moon's gradually increasing distance from Earth, caused by tidal friction, will eventually eliminate total lunar eclipses entirely. In approximately 600 million years, the Moon will orbit too far from Earth for our planet's umbral shadow to completely engulf the lunar surface, ending the spectacular blood moon phenomenon forever. Observing a total lunar eclipse requires no special equipment beyond clear skies and patience, making this astronomical phenomenon uniquely accessible to everyone. Unlike solar eclipses, which demand protective filters and specific viewing locations, Lunar eclipses can be safely observed with naked eyes from anywhere on Earth's nighttime side, offering unparalleled opportunities for public engagement with astronomy. The eclipse observation experience begins hours before totality during the penumbral phase, while subtle, experienced observers can detect the moon's gradual dimming as it enters Earth's outer shadow. This initial phase teaches patience and develops observational skills essential for astronomical pursuits. Binoculars enhance the penumbral phase visibility, revealing the shadow's progression across individual lunar features. As the moon enters the umbra, the curved shadow boundary becomes clearly visible, advancing across familiar lunar landmarks. Mare Crisium, the Sea of Crises, often disappears first during eclipses approaching from the east, followed by the prominent crater Tycho near the moon's southern region. Observing these details helps viewers develop deeper connections with lunar geography. During totality, the moon's transformed appearance reveals subtle color variations across its surface. The lunar limb or edge often appears brighter than the center due to Earth's atmospheric refraction effects. Different regions may display varying shades of red, orange, or brown, reflecting local atmospheric conditions on Earth. These variations provide real-time information about our planet's atmospheric state. Photographing lunar eclipses presents unique challenges and opportunities. Unlike typical lunar photography, requiring fast shutter speeds to prevent overexposure, eclipse photography demands longer exposures to capture the dimmed moon's subtle coloration. Camera settings must be adjusted continuously throughout the eclipse as lighting conditions change dramatically. A successful eclipse photography strategy involves bracketing exposures throughout each phase. During partial phases, exposures of 1/60th to 1/15th of a second at ISO 400 typically capture both the illuminated and shadowed portions. Totality requires longer exposures, often 1 to 4 seconds depending on the eclipse's darkness and desired artistic effect. Composite images showing the moon's progression through the eclipse create compelling visual narratives. These photographs require careful planning to position the moon's path within the frame while maintaining consistent magnification throughout the event. Many photographers use telephoto lenses ranging from 300 to 800 millimeters to achieve adequate lunar detail. Modern digital cameras offer significant advantages for eclipse photography through their ability to capture high ISO images with minimal noise. Mirrorless cameras particularly excel due to their electronic viewfinders, which allow real-time exposure preview even in low-light conditions during totality. Scientific observations of lunar eclipses continue contributing valuable data to multiple research fields. Timing the eclipse phases helps refine lunar orbital models and detect subtle variations in Earth's rotation rate. Temperature measurements of the lunar surface during eclipses reveal information about lunar thermal properties and regolith composition. Spectroscopic analysis of eclipsed moonlight provides unique insights into Earth's atmospheric composition. By comparing the spectrum of sunlight to eclipse light, researchers can identify absorption features caused by atmospheric gases, aerosols, and water vapor. This technique offers a space-based perspective on Earth's atmospheric properties. The eye. Historical and cultural significance of lunar eclipses spans every human civilization. Indigenous cultures worldwide developed sophisticated eclipse mythologies, often interpreting these events as cosmic battles or supernatural interventions. These cultural perspectives remind us that astronomy serves not only scientific purposes, but also fundamental human needs for understanding our place in the universe. Educational applications of lunar eclipses extend far beyond astronomy. These events provide opportunities to discuss atmospheric physics, orbital mechanics, electromagnetic radiation, and mathematical cycles. Teachers worldwide use eclipse events to engage students with hands-on science experiences that demonstrate theoretical concepts through direct observation. The accessibility of lunar eclipses makes them powerful tools for inspiring scientific careers. Many professional astronomers trace their initial interest in science to childhood eclipse observations. These formative experiences demonstrate how public engagement with astronomy can have profound long-term impacts on scientific literacy and career choices. As we continue exploring the universe through increasingly sophisticated technologies, lunar eclipses remind us that some of nature's most profound lessons remain visible to the naked eye, connecting us directly with the cosmic forces that govern our existence in this vast and beautiful universe.